balls of the fermions. As far as explaining the forces interacted with throughout the fermion family.
So, as far as how all the subparticles interact with the atom, I think you explained how the electron moves from one orbital to the other one because of some of those other particles you explained about. Can you?
Oh, so we're going back to the atom?
Well, just for a brief second, so
Yeah,
explain that to me.
that's fine. So, again, we have the orbitals, but there's a quantum mechanical phenomenon known as quantum leaping. So what this is basically the electron jumps to a higher or lower orbital within the atom. The electron can either gain energy and jump to a higher energy orbital, or it can lose energy and emit a photon. It can do that because of quantum electrodynamics and jump to a lower orbital. So let me use an example. If we're still using the 1 electron volts, 3 electron volts, and 5 electron volts energy levels. So let's say the electron is on the 3 electron volt energy orbital, and it emits a photon of 1 electron volt. So since it gained 1 electron volt of energy plus 3 that it initially had, it has 4, but it can't have that since the atomic energy orbitals are quantized. You can only have 1, 3, or 5. So the electron re-emits the photon. It's as if the electron was unaffected by the photon. So if the electron was to gain 2 electron volts from a photon, being on the 3 electron volt energy level, it would have 5 electron volts of energy. And I said there are 1, 3, and 5 in the example.
So we jump to the 5 orbital.
Yes.
Okay,
since there's a taker for the 5 energy, the 5 electron volt energy orbital.
So it sounds like the electron volt energy level of an electron is made up of its photon. It's composed of photons then. Or the photons give it the electrical energy, right?
What do you mean?
So
these are separate electrons. These are electrons outside of the atoms that got lucky and hit the electrons.
Okay, but when you say photons, right? When an electron having an additional photons, that means that
additional photons.
Okay.
Like the ones that are outside of the
Yeah.
Oh.
So is that what happens? These are photons that are outside of the atom and hit a specific electron. So is it the photons that actually carry the energy for the electrons? In other words, when an electron loses a photon, it loses energy. When it adds a photon, it adds energy.
Yes.
Okay.
But I thought for a second you were asking if the energy orbitals were composed of photons.
No. I'm talking about the electron. The energy in the electrons is made out of photons. And photons, you said, are light.
Not necessarily made out of photons. It can gain energy by absorbing a photon, but it can also lose energy by so not to say that the electrons are composed of photons, but when an electron loses energy, that energy has to manifest itself into something, which in the specific sense is the photon.
Okay.
Electromagnetic radiation. So in the same way that the electron can gain energy, so I left off where I said the electron was initially on the 3 electron volt energy level, and it gained 2 electron volts, so 2 plus 3 of course is 5, and it jumped to the 5 electron volt energy level. So in the same way it can lose energy, but it's easier to lose energy. What I mean by this is not necessarily easy, but the electron can lose any amount of energy it needs to jump to the smaller orbital.
Yeah.
Not the smaller orbital, but the orbital of less energy.
Yeah.
So if it was on 3, so right away, if it was to lose energy, if the electron volt within the one, yeah, so we're still going with the 1 electron volt, 3 electron volt,
Yeah.
5 electron volt. So if the electron was to jump to the 1 electron volt level from the 3 electron volt orbital, you would see like the electron would of course the electron has to lose weight.
Mhm.
It has to lose energy.
Or mass or something.
No, not mass. Not.
Well, you said weight.
I was being funny.
Okay.
So the electron has to lose energy to get from the 3 electron volt range to the 1 electron volt range.
Okay.
So it emits a 2 electron volt photon.
Okay.
So,
So what happens to that photon? Where does it go?
it just
goes anywhere?
yes.
So it can go to a different atom, a
whatever,
different.
probably a different atom.
So that can mean a different atom in a different element.
I don't know wherever the light goes.
Okay. Gotcha. Okay. There could be anywhere. So how does science discover all these subatomic particles or composite particles?
So how do we? So what are you asking? How do I know how to like how do these particles break down into smaller?
Yeah,
particles?
like
how do we know
how has science found out about these particles?
particle accelerators?
Okay.
So
Yeah, tell me about particle accelerators.
what a particle accelerator does is this is how a particle accelerator works. So you have a large metal tube with strong magnetic fields, so that the particles don't crash into the walls, so that they stay wherever they're guided. So with particle accelerators, you have again a long circular tube, a long tube with with strong magnetic fields within the tube, like in a circular path. So what happens is these particles are of course accelerated to relativistic speeds. They're accelerated to energies like very high energies, but they're accelerated to velocities around the speed of light. Not necessarily like in general relativity and the theory of relativity, you can approach the speed of light, but you can never get there. As close as you can never get to the speed of light.
Okay.
So these particles are accelerated to around the speed of light, and they are crashed together in high energy collisions. And what happens is, if they have constituents, if they're crashed together at high enough energies, they can spit out different particles that you never knew were there. They can spit out new particles.
So is that how we found all these different constituents to the
Yes.
subatomic particles?
Yes, we found quarks by colliding protons or neutrons, protons and neutrons within these high energy particle accelerators. I can name two particle accelerators off the top of my head: Fermilab around Chicago, and the LHC with the Large Hadron Collider in Geneva, Switzerland, with the company CERN.
Okay. So that's CERN.
Mm.
So CERN is the company, is not the collider itself. So what's the collider's name again?
The Large Hadron Collider. The
Okay.
CERN itself is for atomic research, nuclear research.
Okay. Okay. Interesting. So you were telling me about string theory and how it says that these particles are not mass, they're energy instead. What is that about?
Oh, it's not that they don't have mass. It's so string theory in the long run suggests that string theory as well had its own history behind how it was, like string theory also has a history but it has a history of how it was built up from these previous versions of string theory.
Okay, but
But I'm
don't.
not gonna get into
Yeah,
that.
please don't.
That's irrelevant
Okay.
at least this video. I can make that in a separate video. I can describe it in a separate video. But string theory in the long run suggests that all matter that composes the universe, all matter that makes up the universe, it breaks down essentially to vibrating filaments of energy, vibrating strings of energy. There's no question of how string theory got its name.
Okay. So, matter is energy, or is matter is compulsive energy? What does that mean exactly?
Oh, so you've heard of E equals mc squared, right?
Yeah.
That's a famous physics equation, and it's on the side of special relativity. So E equals mc squared. So special relativity describes mass energy, and general relativity is more associated with kinetic energy. It's the energy that is associated with moving matter.
Okay.
So special relativity describes the motionless. It
Okay.
describes the energy that matter has when it's not moving, which is,
Okay.
of course, mass energy.
Okay.
So with E equals mc squared, of course, mass can be exchanged with energy. Mass and energy can be interchangeable. They're equal to each other by a factor of c squared, which is the light speed constant squared.
Okay.
So that goes for mass energy, but also string theory suggests that these particles so what string theory in this case does is, aside from relativity, string theory proposes that these elementary particles can be replaced by specifically vibrating closed strings of energy.
Okay.
So you can decipher particles by how these closed strings vibrate.
Okay. Okay. Perfect. Okay. Okay.